Welcome to The Explainer. Today, we're putting on our senior architect hats and mapping out a solution to a massive tension in production systems right now, which is managing AI prompts at scale. Honestly, if you're a Java developer trying to put AI into production, you've absolutely felt this friction firsthand. It's a real headache. So let's unpack exactly how AI Fabric steps in to solve it.
Here is our roadmap for today. 1. The prompt management dilemma. 2. Bundles and ordered overlays. 3. Resource keys and fallback. 4. Prompts versus security policy. 5. Avoiding incorrect architectures. And 6. Regression proofing and testing.
Section 1. The prompt management dilemma.
Right, so we have to start by establishing the core tension here. Prompts in a production framework desperately need two properties that are basically always at war with each other. On one side, your framework defaults must improve centrally over time as the underlying models evolve. You want those free upgrades, right? But on the flip side, your specific application has to completely own its domain language and its special follow-up behavior. It's kind of a trap. If you just copy and paste every single prompt into your app, will you completely destroy the framework's ability to update them? But if you try to just edit prompts inside a dependency, you lose all your domain control. You are totally stuck.
Section 2. Bundles and ordered overlays.
To actually solve this tug-of-war, AI Fabric introduces a really elegant architecture using versioned class-path prompt bundles, combined with ordered overlays. This packaging method is literally the secret sauce of the whole operation. It allows your individual application to genuinely own its domain delta, the specific parts it actually needs to change, without sacrificing those absolutely crucial central framework updates we just talked about.
Think of it a bit like a giant puzzle. A curated support module supplies the base. These are coherent, highly safe defaults, giving you support-safe intent handling and evidence-grounded answers right out of the box. Then your application overlay just snaps right into place, adding only its specific delta. Maybe it adds some recent turn follow-up rules or a stricter answer projection tailored just for your specific app. And because you only overlay that tiny delta, the foundational, untouched action selection templates, they still safely update from the core framework in the background. It's the best of both worlds.
Section 3. Resource keys and fallback.
So let's look at the actual mechanics. Every single prompt in the system isn't just, floating around in some random folder. It is defined by a very strict taxonomy, a resource key, made up of its family, its version, and its name. This precise categorization is the absolute foundation that makes the entire overlay architecture function.
How does the resolution actually happen in practice? Well, let's use the Support Knowledge Assistant as our example here. Fallback resolution operates as a strict step-by-step sequence. First, the system checks for the template in v1-core support. If it's missing there, it steps down to v1-support. Still missing? Okay, it falls back to the framework base v1. The rule is elegantly simple. The first existing complete template it finds wins.
Now, I really want to highlight a massive distinction here, so lock this in. AI Fabric uses whole template selection. This is not a markdown patch. You aren't surgically injecting a random sentence into an existing prompt. The golden rule is that the application should only add the resource keys whose complete behavior it genuinely owns. If you don't own the whole template's behavior, just step back and let the framework handle it.
But hey, what happens when things go wrong? Say an expected application template gets renamed accidentally. The app actually still starts safely because the resolution just smoothly falls back to the curated support version. Now, your regression test will fail, which is exactly what it should do, but the app itself survives. Crucially, though, if no candidate exists in the fallback chain at all, the system fails clearly and visibly. It literally throws an error rather than trying to hallucinate a prompt template out of thin air, which would be a nightmare.
Section 4. Prompts versus security policy.
We have got to draw a hard architectural line here. Prompt rules are inherently probabilistic, while security policies must be deterministic. Always. Prompts are there to guide probabilistic output, so they can tell a model to use a recent conversation, maybe avoid outside facts, or emit structured JSON. But they absolutely cannot perform deterministic security controls. Actually, scratch that. They shouldn't even be allowed near them. A prompt cannot authorize a write, it cannot grant tenant access, and it cannot validate parameters. Those vital, rigid controls must remain strictly locked down in your authenticated context, typed action schemas, and execution services. No exceptions.
Section 5. Avoiding incorrect architectures.
So now that we know what right looks like, we have to ask ourselves, where do standard prompt architectures typically go totally wrong out in the wild, especially when developers don't lean on a structured framework like AI Fabric?
There are 3 really fatal traps developers fall into. First, copying every single framework prompt and just editing one line. This permanently strands the app on old defaults. Second, placing security solely in probabilistic prompt pros, which, as we just discussed, is a massive vulnerability. And third, exposing full prompts through a public health endpoint. All 3 of these are catastrophic because they completely shatter your ownership boundaries and just recklessly expose your internal system mechanics to the world.
Section 6. Regression proofing and testing. Let's talk about locking all this down. Because large language models inherently change their responses all the time, you should absolutely never assert exact generated pros in your automated tests. Running an optional real provider check? Sure. That can reveal model behavior changes, which is great for observation. But remember, it is strictly an observation. It is not your release contract.
Instead of those brittle prose checks, your regression proofs must assert the strict deterministic properties of AI Fabric. Test the candidate order and ensure the resolved version is exactly what you expect. Verify that required placeholders and critical safety rules exist within your templates. Prove your fallback behavior for untouched keys. Prove your class path packaging is correct, and rigidly ensure the complete absence of prompt bodies from any public diagnostics. These are the rock-solid properties you can actually rely on for a stable production release.
And this brings us directly to your actionable next steps. In LabProd 03, you're going to put this exact theory into practice. You'll add the application answer template, test the overlay first and base fallback resolution we just mapped out, prove the resource is properly packaged right in the jar, and expose only the safe version diagnostics. Applying this exact ownership discipline right here is what paves the way for safely migrating your application data and vector evidence later on.
As we wrap up this explainer, I want to leave you with a critical architectural question to evaluate in your own codebases right now. Are your probabilistic prompts truly, completely separated from your deterministic security policies? Getting this boundary right is literally the difference between a brittle, insecure application and a resilient, centrally updatable AI architecture. Thanks so much for joining this whiteboard session, and I'll see you in the next explainer.